we examine the parametrization of some common curves. This is based on your textbook. Pattern number 1, to parameterize y equals f of x. As x runs through some interval I, we let x equals t and y equals f of t, and let t run through the interval I. For example, y equals x squared minus 3x from x equals -3 to x equals 5. We can see that y is a function of x. We let x equals t and y equals t squared minus 3t. We get the equation of y by replacing x by t, and t is between -3 and 5, including the endpoints. Another example, y equals 3x minus 16 from x equals -3 to x equals 8. Again, y is a function of x. The pair of parametric equations is x equals t, y equals 3t minus 16. -3 is less than or equal to t, and t is less than or equal to 8. Pattern number 2, to parameterize x equals g of y as y runs through some interval I. Let x equals g of t and y equals t, and let t run through the interval I. For example, y equals f inverse of x, where f of x equals x cubed plus 2x plus 1. Since f inverse exists, f is a one-to-one function. Y equals f inverse of x implies that f of y equals x. We interchange x and y and solve for x. We get x equals y cubed plus 2y plus 1. Then we replace y by t and get our pair parametric equations. X equals t cubed plus 2t plus 1, y equals t, and t can be any real number. Pattern number 3, to parameterize a directed line segment with initial point x0, y0, and terminal point x sub 1, y sub 1. We let x equals x0 plus x sub 1 minus x0 times t, and y equals y0 plus y sub 1 minus y0 times t. For 0 is less than or equal to t, less than or equal to 1. For example, we parameterize a line segment that starts at -2, -7, and ends at 5, 3. In this case, x0, y0 equals -2, -7. X sub 1, y sub 1 equals 5, 3. Using the formula, we have x equals -2 plus 5 minus -2 times t, y equals -7 plus 3 minus -7 times t. Simplify them, we get x equals -2 plus 7t, y equals -7 plus 10t. T ranges from 0 to 1, including the endpoints. Pattern number 4, parametrizing the equation of an ellipse centered at hk. X minus h squared over a squared plus y minus k squared over b squared equals 1, where a and b are different and they are both bigger than 0. We let x equals h plus a cosine of t and y equals k plus b times sine of t. For t ranges from 0 to 2 pi, including the endpoint 0, excluding the endpoint 2 pi. For example, we will parameterize the equation 25x squared minus 50x plus 9y squared minus 72y equals 56. We will complete the squares. Pull out the common factor 25 between the first two terms. We have 25 times x squared minus 2x. Pull out the common factor between the third and fourth terms. We have 9 times y squared minus 8y equals 56. We complete the square of the first parentheses. We divide negative 2 by 2 and then square the result to get 1 inside the parentheses. 1 times 25 is 25. In order for the equation to stay true, we add 25 to the right side. We also complete the square inside the parentheses involving y. We divide the coefficient of y, which is negative 8, by 2, and then square the result. Thus, we add 16 inside the parentheses. 16 times 9 is 144. In order for the equation to be correct, we add 144 to the right side also. Writing both parentheses as squares, we have 25 times x minus 1 squared plus 9 times y minus 4 squared equals 225. We then divide both sides of the equation by 225. We have x minus 1 squared times 25 divided by 225 plus 9 times y minus 4 squared over 225 equals 225 over 225. After that, we simplify to get x minus 1 squared over 3 squared plus y minus 4 squared over 5 squared equals 1. Comparing this with the standard equation of an ellipse, we have hk is the same as 1, 4, and a equals 3, b equals 5. We substitute this information into our formulas to get the parameterization. X equals 1 plus 3 cosine of t. Y equals 4 plus 5 times sine of t. T ranges between 0 and 2 pi, including the endpoint 0, excluding the endpoint 2 pi. It is a good practice to always check the answer. We will substitute x equals 1 plus 3 cosine of t and y equals 4 plus 5 sine of t into the equation 25x squared minus 50x plus 9y squared minus 72y equals 56. We will compute x squared first. X squared equals 1 plus 3 cosine of t squared equals the square of the first term, which is 1 squared. That gives us 1, plus 2 times the first term times the second term. 2 times 1 times 3 cosine of t gives us 6 cosine of t, plus square the second term, which is 3 cosine of t squared. It gives us 9 cosine square of t. We will also take a look at y squared first. It equals 4 plus 5 sine of t squared. Square the first term, we get 16, plus 2 times the first term times the second term. That gives us 40 sine of t, plus the square of the second term. That gives us 25 sine squared of t. The left-hand side of the equation equals 25x squared minus 50x plus 9y squared minus 72y. We will take a look at each term and organize our computation to make it easier. For the first term, 25x squared, we have 25 plus 150 cosine of t plus 225 cosine squared of t. For the second term, negative 50x, we have minus 50 minus 150 cosine of t. For the third term, 9y squared, we have plus 144 plus 225 sine squared of t plus 360 sine of t. For the last term, negative 72y, we have minus 288 minus 360 sine of t. Doing the computation vertically, we have negative 169 plus 225, which is 56. That equals the right hand side. That means our parametrization is correct.